Alright, so today we're very happy to have Martone from King's College London, and he's going to talk about tell us about mapping out superconformal theories. Mary, you can take it away.
Okay, thank you. So it's wonderful to be back in New York. It's been only 6 months I left, but I really miss it a lot. So thank you so much, and in fact, I'll try to impress you so that you can invite me again. Spend some more time. Without my wife loves London, right? Okay, great. So the idea is that I want to kind of give you an outline of some recent developments on the quest of classifying superconformal field theories. I will basically discuss mostly the four-dimensional case. I will basically only start by saying something more broad in different dimensions. But the bottom line is that there's been a huge amount of progress, and it's actually possible to be able to classify superconformal field theories. I will not spend any time justifying why that's a smart thing to do. Maybe I'll just add one sentence, and the general idea why it's useful and smart, perhaps, to try to solve the classification problem of superconformal field theories. Of course, if you can classify something, it's always smart to do it. But even more beyond that, it's basically in the idea that we really want to try to study systematically the space of quantum field theories, but that's too hard. So the question of classifying superconformal field theories is perhaps one of the easiest things you can aim at doing. So this talk is based mostly on these 4 papers, but in reality many more. And there's a long list of collaborators. There is no real junior collaborators that are looking for jobs, so that's why I writing them up. And the plan of the talk is the following. I'm going to start by giving a very short review of superconformal field theories and how constrained they are. In fact, there are theorems that tell you that superconformal field theories can only exist up to 6 dimensions. That's kind of remarkable, and I'll kind of give you an overview of how it's derived, so that you really get a taste that this is really special. And then we'll start focusing on 4-dimension. We'll give you some generalities, and in particular, I'll describe to you what I consider the defining data for 4-dimensional superconformal field theory. By the way, I'll use aCFTs as an acronym, just to not have confusion. And I will focus on 2 types of operators that I call Coulomb and Chur. I will define them later. And that will really give you kind of a hint on how to possibly do a systematic search, which has been partially implemented, at least in this latest paper. And I'll give you also a sense of what has been, what is known so far. The last part, Josh, my miss. What do we know about this work? But anyway, so at any point, of course, you can stop me. Great. So it's well known, assume that in any dimension, in dimension D, the conformal group is SO2 comma D. Okay. So here now when we have also the precedent supersymmetry, with the precedent supersymmetry, SO2 comma D is enhanced to a supergroup G, and which has very special property, right? So basically asking what are the possible supergroup G for which this enhancement makes sense, tells you that superconformal field theories, for example, you can derive from and I'll show you in a second, from asking what are the compatible ways in which a conformal group can enhance a supergroup G, will enable to derive you very, very strong results, which supergroup aCFTs can only exist in D smaller than 6, or equal to 6. At first, this was a result that was derived by Nam in the 70s. That was not very much appreciated because people thought that really the correct result should have been D smaller than equal than 4. So they thought that this was like kind of a curiosity. But lately, we actually were able to construct aCFTs up to dimension 6. So how does that work? Basically, the point is that the bosonic the bosonic part of G, of the supergroup G, will be of the form SO2, D, for it to be an enhancement, or is a kind of a supergroup that gives you superconformal invariance times some K, where K, let's say, is a compact Lie group. And the point here is that K, for everybody that is familiar with supersymmetry, this will be kind of identified as the R symmetry. So some other bosonic component of your aCFTs. So this K will be the R symmetry of the aCFT. Okay. Now the point is that the fermionic part of G, they have to transform in the spinor representation of SO2, D. So what you can do is basically take the list of supergroup and check what are those that have SO2, D as a component of its bosonic part, and check whether or not the fermionic component of G do respect this second condition. It might appear that it's not very strong, but in fact, if you actually do a systematic search, you find just a finite set of solution. And let me just state why that's the case. And they actually rely on very exceptional properties of kind of low rank groups. So in particular, for example, there is one supergroup which is called the OSP 2, D / R. This is a group, right? And the property of this is that the bosonic part is SO2, D tensor SPR. Okay, so you have the first is check. It's easy, right?
USPR.
USPR. Sorry, yeah, that's what I mean. With SP, there's always a set of conventions, but I agree. That's more correct. And then the point is that generically, if for any D, the fermion actually transform in the vector representation of SO2, D. Okay. So the second component here, the second condition is not respected for generic D. But of course, if you are up into your Lie group theory, you realize that this thing, but for D equal to 6, there's a special property of SO2, 6, which is called triality, that tells you that basically the vector is the same as the spinor. Okay? So for a very exceptional case, which is D equal to 6, you find that in fact this supergroup does satisfy both property. Okay, and this in fact, in general, this OSP 2, 6 / R, this is the superconformal group of aCFTs in 6 dimensions. Okay? Questions?
So this property is independent of the signature of the SO because it's valid for SO8, right? Then there you have a Majorana invariant property that says that you have, say, 8 real degrees of freedom.
Sure.
But for an arbitrary signature, when the difference between space and time is not 8.
I understand. So it's not Minkowski, you're saying, basically, like.
And yeah, I mean, the difference of space minus time is 4, not 8. Right? So don't you have a doubling? Are the fermions real at Majorana?
I see.
So at the same time.
Yeah. So I don't know.
Here is you impose the symplectic Majorana condition used together with the USP indices.
I see.
Yeah.
So, okay.
You don't have a separate. You don't have Martone just on the spinor indices. You have the synthetic Martone that combines with the radical combination in the USB.
So the fact that you have USB is
That's right.
important.
That's right.
Okay, great. So anyway, so the details of this is not important, but you can see already that there's a very, very special, very constrained game here. You can't really play around much. And in fact, basically you are restricted to a very small set of possibilities of dimensions and supercharges that give you superconformal field theories. Now, for the rest of the talk, we will only interested in aCFTs which have 8 supercharges.
Can I ask about this?
Sure.
So, what really goes? What are the assumptions about this aCFT? For instance, is unitarity needed for this argument?
In this
Right, so
no, I'm not. I mean, this is purely group theoretic.
So even if I don't insist
No, in
on
fact-
unitarity, then
But that's in some sense that's what I was saying, because so when it first appeared, that was the kind of the results that was noted, that kind of was derived from group theory. But people really believed that the correct answer for the unitary superconformal field theories was this, right? So it seemed just a kind of an interesting group theoretic exercise, but that had little to do with actual field theory. And then later, superconformal field theories, there has been string theoretic argument that showed that in fact there are unitary superconformal field theories existing in dimensions higher than 4.
But I think that in a sense unitary is required and Coleman-Mandula, right? Because when you write a decomposition, you're using Coleman-Mandula.
Yeah, that's true. But
so, for instance, the fact that you don't have a big group that mixes the space-time.
sure. That's I mean in identifying basically these two conditions.
And when you write that the bosonic G should be a product, right?
Of the
times
asymmetry.
the internal one.
so you think unitarity enters somewhere there?
But yes, because why keep compact otherwise, right?
But would Coleman-Mandula apply in the case you don't have asymmetrics?
Yes, they also have a superconformal version. I mean, Coleman-Mandula has to, in the non-compact, with massive particles, they prove, quote unquote, that the group is Poincaré times an internal group, and for massless particles, they prove that you could have conformal times internal.
I see.
No mixing of the indices.
But are there examples of larger than 6 non-unitary aCFTs?
Yeah, but I think this argument will also work, right? Because this is just group theory statement.
But
Yeah,
my
but
K
K is
can be
compact. K is
non-compact, right? For non-unitary theory.
I mean, the fact that you use SO2D already says that the group is conformal, and that already includes unitarity. Otherwise, you could have SO4D minus 2, right? You could have a lot of other things if you don't impose unitarity. Right? You
No,
could
but
have
that's
K non-compact.
no, but it's just the in Lorentz signature, right? So I can.
No, I understand. That's a great question. I don't know if so. I don't know of any. You're saying if you lift in unitarity, can you go above 6 temperature?
Right.
That's
I don't see why.
But the
Yeah.
other dimension of the spinors would be too big to be spinor representation. SO8.
Well, I mean, you have some reductions when space minus time is a multiple of 4 or 8. So if you play with the space and time dimensions, you may have some extra reductions, but probably irrelevant.
perhaps we should.
Yes.
Great. So then basically, if you restrict to 8 supercharges, then there's a kind of a canonical list of superconformal field theories called 6D 1,0, 5D n equal 1, 4D n equal 2, and 3D n equal 4. Now you can ask what are the K here, and the answer you get is SU2, SU2, for the third one, SU2 cross U1, and SU2 cross SU2. So what I would argue is that in what makes largely what makes 4-dimension special for my purpose of building up the classification scheme really is this extra U1. This extra U1 is really makes makes 4D special. And we'll see that in a second. And really, it allows you to define another set of operators and extra constraints that allow you to start from the bottom up and trying to ask what are the possible 4-dimensional equal to aCFTs that are allowed. Let me remind you that there are classification schemes in 5 and 6 dimension, but they are very different nature than the things that I'm saying that today. The thing that I'm going to say today is basically very field theoretic inspired, meaning like I'm assuming that there is superconformal invariants, and that implies certain structures. What are the set of possibilities that are allowed by those structures? In 5 and 16, instead, all the classification schemes are really in terms of string theory and F-theory realization. So there's an underlying assumption that every single aCFT has to be realized in F-theory, and then the classification goes. So what I'm arguing is this extra U1 is really needed to be able to, instead, not assuming necessarily that there has to be a UV realization in string theory, but really asking from the bottom up what is allowed. You have questions? No?
Me?
Yeah.
No, I do like it.
Yeah, no, because sometimes the finger went up.
Sorry, Mario. About 5 dimension, there are people who are trying to do this bottom-up procedure as well by studying the Coulomb branch. Of course, the connection to the CFT data is less clear because of the Coulomb branch.
Yeah, but the problem is exactly what you're saying, right? In 5D, the Coulomb branch is real, right? Yeah. So, I mean, you can set up the problem in any
like the intricator Moore cyber condition.
Sure.
Is some IR consistent condition on effective field theory.
Exactly. There are some conditions, but it's hard to really push it much beyond.
But there are work, for example, to classify rank 1 theory this way.
Sure. I agree. But you know, for example, in a genetic setup in 5D, it's hard to imagine, right? In terms of, for example, if you have a 2-dimension.
Yeah, you have more tools important, of course. Yeah.
Any more questions? Okay. So that's what, and of course, you know, 3D things are kind of the philosophy here is that you know, given an aCFT in D dimensions, there's many ways to reduce it to D-1 dimension. So you want to go to the highest possible dimensions to your classification scheme that allows you to build up enough constraints to classify things, because the number of theories you expect to grow as you go down in dimension. And so that's why 4D it's really kind of I would argue the key dimensions to try to do this exercise.
So this U1, if I'm reducing from 6D, this U1, how do I see where it's coming from already? Let's say
yeah, you have to see it in terms of like of how the multiplets, the 6-dimensional multiplets, kind of decompose.
Mm-hmm.
Yeah. So for example, in 5D, there is a real scalar that becomes complex.
But it's coming from the KK symmetry, right? If you compare it on 2 direction, that's coming from the U1 rotating the compact direction.
So if I go from 5D to 4D, it's really the
KK.
It's a circle, right?
Yes.
Exactly.
Mm-hmm.
That's what it comes.
I mean, from 60, I think so you have SO5 and 60. You'll break it to SU2 cross U1 just to do the topological twisting. The U1 that you get there is the one that's presumed the topological twisting. But so what would be the obstacle if I wanted to do this in 2,0? I just use SO5 as SO2.
Right. No, so the question is that you want to set up a problem of that means of low energy constraints on your problem that only assume the fact that there is the amount of supersymmetry and superconformal invariance that you have assumed, and then that's kind of that constraining system has to be so tight that you can build it from the bottom up.
But maybe maximum question is, if you study this same the problem for 2,0, and then from the same approach, like from consistency of effective action on the moduli space, that you can do, and that has been done. And most recently, the revisited from the paper of Thomas, Dimitrescu, Clay, Cordova, and Chi.
Right.
And you recovered AD classification that you can also do right from string theory. But it's, I mean, what Mario is describing here is much richer.
It's much richer, yeah. That's okay. Okay, so I want to now kind of be a little bit clear on how we're going to go and search for these aCFTs, and in particular, what is the data that I claim would define an aCFT. For example, one of the remarkable claims that it's, I don't think I have a sharp argument, perhaps the people in the audience here can help me, but I would claim that an aCFT in 4 dimensions can be identified by just a finite set of rational numbers. And I'll try to make that claim. The finite set of rational numbers identifies an aCFT. There's strong, I mean, I don't have a full proof, but there's strong, so. Cool, okay, first of all, let's kind of remind ourselves how you would, so this is 2.2 for the aCFTs. So first, let's do the exercise of trying to define abstractly a CFT. I'll be very quick because you're all expert. So one way to discuss a CFT abstractly is in terms of its algebraic operator, and which are identified by spins, the quantum numbers, scalar dimensions, which I will label it as delta I, and perhaps some global symmetry. So those quantum numbers identify your operators, and then let's say you assume that you're looking at this an aCFT where I'm doing here the presentation for scalar operators, the generalizations for spinning operators is more technically complicated or straightforward. For scalar, then you know that, for example, 2-point correlation function of OJ y, x1, x2. This is delta ij, so it's completely fixed by conformal invariance. Okay, so 2-point correlation function. Once I start by giving you the set of operators, the 2-point correlation functions can be written completely down because of course, here I'm making a choice of basis for your scalar operators. Apart from that, that's basically fixed by conformal invariance. And then the entire data of your CFT, it's encoded into basically the 3-point function. Because that can be fixed almost entirely by symmetry, but there is something in the numerator which are the OPE coefficient that is truly some theory dependent data. And then the denominator it's written in terms of some CFT, some symmetry factor, so to speak. And the rest is the physical implementation.
And these are conformal primaries.
These are conformal primaries. Yeah. Okay. So one way to then define a CFT in abstract is to provide a set of.
There's another for that will do this.
I see. I understand. There is.
I think it's.
Oh, this goes up. Thank you. Right. So you can then define a CFT, but just abstractly by the set of OP coefficients and the algebraic operators, the quantum numbers, and so forth. So a CFT, let me write it down. You can think of as a set of operators and lambda I1, I2, I2. So that's quite a bit of data that you need to do to specify the theory. There are some kind of numbers that capture the number of degrees of freedom of the CFT, which are particularly easy and particularly handy. Just introduced them for completion because I'm going to refer them to later. And those are the so-called conformal central charges, or also conformal anomalies. And those are defined in terms of the stress tensor of the theory, and if you have a global symmetry, then in terms of the currents. And those are defined as follow. You take the stress tensor of the theory, you consider the 1-point function on a curved background, and this is equal to some c, maybe since I have color chart. You can use that. So there's a number, a special number here called c. There's some prefactor. It's the file tensor square, then plus some other number a over 16 pi squared. It's the Euler tensor. And so A and C are the conformal center charges. And again, here, really the theory is defined by an infinite set of data, but C and A somehow are two numbers that in some ways capture in a much more succinct way the numbers of degrees of freedom. And then there's a third one, which is the flavor central charge, which is given by the the OP between the flavor current. So J's are the flavor current, so there's a global symmetry. And then here you have here, right, a lot of things there.
Sorry. So dumb question. So I would expect that the trace should be proportional to Ricci, but that's only, I mean, I maybe am remembering in string theory that was a trace anomaly because one of those tensors or the Ricci scalar is the other characteristic, or in general in moral dimensions, Ricci does not appear and other tensors from gravity appear in that formula.
Yeah, this is, I mean,
This
is just general. Yeah,
like in 2R would be playing the role of Weil.
And Euler. Yeah, but of course, I mean, for a conformal anomaly to be non-trivial, it must have dimension 4. Right? Yeah. So in 4 dimensions and 2 in 2 dimensions. 2 dimensions you have, say, Riemann. In 4 you have Weil, and this, of course, doesn't take into account things that vanish on shell.
Yeah, of course.
All this building block can be expanded powers of the Riemann tensor. So, for example, this will be quadratic in the Riemann tensor. It will involve Ricci squared in particular, but it's some particular combination that's consistent with velocity.
Because it's better being conformal invariant than normal integrated one. So this is would be the same if if you put your theory on a gauge field background and compute the divergence of J, or is it a different number? This K.
This is I'm perhaps not understand. This is just the global conformal anomaly.
Yes. But the K that you have there.
This K, yeah, the global flavor anomaly. Yeah. J are kind of global currents.
Yes, but if you take an external fixed spectator background field, exactly like you have an external fixed spectator metric, would that K be the same that appears in the mu J mu? I mean, in the divergence of J, or would it be a different number?
Oh, you mean if you actually put a fixed background of for the global current?
Yes. No. So there's no pure. So it's a non-trivial fact. There's no pure. There's no pure flavor symmetry anomaly. This is going to show up in the next anomaly with V1R. So it's the A non-invariant 3-point.
Thanks.
So within 2-1 you will have that, and that will show up as a DABC, another term that is not right.
Just a question, like so your flavor group here is the R symmetry, right?
No.
Oh, it's a different.
No, it's a different.
Oh,
it's a different. My flavor group is perhaps an extra global symmetry.
Sorry, can you repeat what you said? Is this K related to some Topham anomaly?
K is related to the Topham anomaly between U1R and the flavor.
Okay.
So if there's a flavor Topham anomaly, then it will show up as coefficient of DABC. But DABC is absent in any 14U2 theory. It's a consequence of the enhanced superconformal symmetry. They will be present in 14U1.
So the two anomalies is a Bardeen anomaly, right?
I mean 3.1.
Yeah, 3.1.
Yeah, the one computed by Bardeen, Adler, like 20, 30 years before Topham.
Yeah, unfortunately the name.
The usual rule of theoretical physics. Something is named after the last person who discovered it.
You made this exact complaint. I've heard you make this exact complaint.
Yeah, and Gregory.
Oh yeah, maybe it was Greg.
I can complain to you, right?
It was Greg. Yeah, it was Greg.
I didn't actually talk about Circuit mentioned.
Okay, so good. So then for in the case, so what happens if instead we have 4D and equal to superconformal symmetry, then there's clearly one obvious simplification, the fact that now the operators and the primaries are organized in supermultiplets, so there's some internal symmetries in the theory, but that's not the thing that really allows you to basically go from an infinite set of CFT data, something that I'm telling you that to a bunch of rational numbers. So let me try to explain instead what I think are the real kind of advantages of the mathematical structures that arise if you have 4D and equal to superconformal invariants. So first of all, we have to discuss a little bit the multiplets that are allowed in n equal to aCFTs. Now, I will label by the quantum numbers the superconformal primary of the multiplet, so the rest of the multiplet can be filled in by actions of the superconformal transformations and supercharges. And so I will denote, which is basically following notations by Clay, Cordova, and Thomas Dimitrescu and Karen Turnigator, but I will denote every multiplet following way, where L and L prime are the spins of the primary, of the superprimary. Then R, capital R and little r are the SU3R cross U1R quantum numbers, and delta is the scaling dimension of the primary, of the superprimary. Okay, good. So
This means this means under the SO4 subgroup of SO2, 4.
yeah, that's what I mean.
Not the usual speeds.
Not usually, yeah. Good. So then, having set this up, then I want to introduce two multiplets, which are key for our analysis, and this is 0.3 Coulomb and Schur, which are called one the Coulomb branch multiplet, and the Schur multiplet. The names are, well, for those of you who know Coulomb branch, they're obvious. Schur is just a mathematician. Okay, good. So the Coulomb branch multiplet are defined by the following thing. So there's the superconformal primary is a scalar, and then they have one condition, which their scaling dimensions is equal to the U1R charges. Of course, there might be a prefactor. I'm fixing it to be 1, but you can rescale the U1R charge and change this condition, but that's inessential. And then they are singlet on the SU2R. So you can see that it's really thanks to the U1R that these multiplets are there. Without the U1R, then they are only charged basically under the U1R symmetry. That's what I mean. And so I'll denote this as U0 Coulomb, which again, using the same notation as before, this will be something of this kind. And then the Schur operators, those are other operators that satisfy some conditions that are a little bit more involved, but they come from some cohomology business, which I'm not going to review too much about it. But the delta is equal, so they instead carry non-trivial SU2R and U1R charges, and could have non-trivial Lorentz transformation, non-trivial spins, but they have to have the quantum numbers of this kind. So a few important things to get to a sense of why those operators are important. First of all, I'm looking for a fancy job. The Coulomb branch operator can acquire non-zero vacuum exclusion value. Okay, And then
Sorry, are these what are called also vector multiplets?
no, so I mean, in Lagrangian cases, yes, that's good. So perhaps I should give an example of what those are. So if you have a Lagrangian theory, then OCD, for example, is something like trace phi to the n, where phi is the complex scalar of the vector multiplet. But those are much more general names. So those are, I mean, there is a reason why I'm setting up this formalism is because you know, the overwhelming majority of n=2 aCFTs do not have a Lagrangian description. So you have to kind of abstract their properties in that sense. Otherwise, you would have a hard time discussing them. And I'll introduce an example of this, but this would be basically the hypermultiplet. So interestingly enough, the Coulomb branch operators can acquire VEV, and then there's another set of operators that could acquire VEV, which they are basically one kind of necessary conditions for an operator to acquire VEV is that it's a Lorentz scalar, if you're assuming that Lorentz invariance is a good transformation in your theory. And precisely the other operators that can acquire VEV are the Schur operators, the Schur scalars. So if L equal to L prime is equal to 0, then this particular set of this Schur operators, so I call this HP. This is basically Schur operator where they are 0, 0. They have no spin, and those are the other set of operators in your theory that can acquire a non-zero VEV. And HP stands for Higgs-Macher.
Just to maybe to clarify here, you are implicitly also assuming that this VEV preserves supersymmetry. Otherwise,
oh sure, of course.
You cannot supersymmetry evacuate generic well.
Yeah, you can have all kinds of things, and it is really, I mean, this fact that those are the operators that can acquire VEV, it's somewhat in this whole business an assumption in the sense that there is no real first principle demonstrations that you can actually that those are the only ones. And in particular, if you have an operator that's a Coulomb branch operator, it should be in principle a question whether or not it does acquire VEV. We know that it can acquire VEV, but whether it does acquire VEV, it's a separate question, which to my knowledge, it has no first principle understanding. So there's an underlying assumptions. Whenever you have operators of these kinds, then they get VEV, even though.
Meaning that there is a modular space.
There is modular space associated with that. But there's no real, I mean, you could in principle, there's a possibility that those operators could acquire VEV and they don't because of the kind of dynamics of the theory, but that's not something that people have any understanding of how to do. Okay, so let me just now tell you some quite remarkable properties of these operators so that we can understand why the aCFT is kind of so special. For example, one of the problem in classifying CFTs is to try to be able to, from first principle, put some bounds on the quantum numbers of operators. And that happens to be quite challenging. Now, for example, if you describe this Coulomb branch operator, there's a series of properties that you can show that are remarkable and they are in complete infusion rather. First of all, the delta I of those Coulomb branch operators, which are equal to their UNR charges, are rational number. Always rational. This is kind of interesting, but it's not. That means basically that the U1 symmetry is actually U1 and it's not R. The second thing that it's extremely remarkable is that you can write a finite set of allowed values that only depend on the number of them. So if your theory has a single Coulomb branch operator, then, for example, if your theory has one Coulomb branch operator, then this operator, it's scalar dimensions, can only be 1, 6/5, 4/3, 3/2, 2, 3, 4, and 6. It can't be anything else. And there's an analogous set of numbers for any number of Coulomb branch operators. There's a closed formula, in fact, that you can actually compute. Right? And this really, this is really kind of remarkable, and this is in assuming nothing but just superconformal methods. And then the third thing that you can show by this property and a few more is that you can show that the A and C central charges, which are there before, they are necessarily rational. Rational number for n equal to a C.
Mary? Well, the first point, the compactness of U1 does not necessarily imply our charges are rational, right? It just implies they're all common integer.
Yeah, sure. It could be of
For example,
some.
for into one, the elementary charge could be algebraic
square
number.
root, yeah, right. That's true.
So
that is a bit more than that. It is a bit more.
Це finite number, so rational.
Sorry, from 2, how do you prove that?
From 2. So so the way you prove that is using.
It's canonical fun.
From that you prove it by using the fact that those operators acquire bed. So you move out in the modular space of vacuum, and then this space of beds has a particular structure which is described by Sabah-Witten theory, and so you're using really the structure of the modular space of vacuum to find the solution. In particular, Sabah-Witten theory is telling you that the space of beds has some singularity somewhere, and you take a loop around that singularity, and the matrix you pick up is an element of SP to RZ of a particular kind, and therefore you can kind of like translate that condition into the fact that there is a finite number. And so the number of Coulomb branch operators is telling you the complex dimensionality of this modular space of F. So this condition is different depending on the dimensionality of the space of Fs, and that's why you get different set of allowed rational numbers depending on the numbers of Coulomb branch. If you have one complex dimension, you have one solution. If you have two complex dimensions, you have two solutions, and so forth.
So this modular space, they're always kind of non-compact. They all have a direction with series goes to free series essentially.
Okay, so this is a little, so here we're talking about modular space of vacuum expectation value. I think you might have referred to the so-called conformal manifold, which is the modular space of couplings, marginal couplings of the theory, right? Here, because that's what basically the fact that there's an the modular space of couplings is non-compact, that's associated with the fact that there's always a weak coupling limit.
I'm thinking more.
Yeah, for the effective theory, it's also weak coupling, right?
Right. Yeah, because if I go to the
no, right, but it's sure, but
yeah, so it's just free, like
free
Maxwell theory.
It's free Maxwell theory, but it's free Maxwell theory on every point here. You don't have to. That's what I'm saying. You don't. It's not. You don't get weak coupling at infinity.
So it's okay.
That is a property of the conformal manifold, which is the weak coupling limit is.
But outside this wall, right? There's a wall of marginality outside this wall, where you have additional mass of this particle.
Okay, so then I wanted to. The story is actually much more remarkable than this, in the sense that we're just scratching the surface. That you can introduce an invariant of the aCFT that purely depends on the Coulomb branch scaling dimensions of the Coulomb branch operators. So let's say you want an aCFT which has OCB1, 2, and 3, 3 of these operators. Each one of those has some particular scaling dimensions. You look at those numbers, and given these 3 rational numbers, you can define an invariant of the aCFT that more or less alone, just a single number, is, if you're lucky, it constrains the entire theory, but just a single number. I'll go back to this later, but if I have time. But since I have another 15 minutes.
Yeah.
So I mean, there's a lot of places in which there's finite set of rational numbers, but I haven't yet told you why I think the aCFT itself can be defined by a finite set of rational numbers. And for that, we have to look at this Schur sector. That is the other set of operators that we defined. Here, really, this is the Schur sector, and there is a quantity which is associated to this Schur sector called the Schur index.
And so is that what corresponds to Higgs branch or in the cybergrid?
Yeah, yes. So you have to think that the Higgs branch is the scalar component of the Schur sector. The Schur sector is actually a wider set of operators. The Higgs branch is when you set that it coincides with restricting to the scalar part. So in other words, while the Coulomb thing, that's why it's called Coulomb, it's associated with the modular space of the Coulomb branch. The Schur, it's more than just the Higgs branch. It's a Higgs branch.
Is part of it.
It's part of it, but
So the operator is actually copying from the root to exactly on the Higgs branch.
yeah, exactly. Okay, so the Schur index, this is a quantity which is basically lists all the Schur indices in the theory, and it contains a little bit more information in that. This is for the expert. This is just a refinement of the supersymmetric superconformal index, number one superconformal index. So the spirit is the same as having just an index that counts discrete things in your theory, and this thing has a form of this kind. Where basically the C1 counts the number of Schur operator which are identified by, which have a particular set of quantum numbers which is identified by the exponent of Q. So there's a way to repackage the information about the set of Schur operators into just one power series in Q. And the interesting thing is that in the by now famous paper 2013, it was shown that this repackaging of the Schur sector, so just the counting of these operators, it's identified times a prefactor of this kind. It's identified with some vacuum module. Let me just say a special function which satisfies a linear modular differential equation. Okay, so there is this kind of remarkable thing that apparently modular transformations enter in your 4D story via this Schur sector. So why is this why is this remarkable? Because each one. So if you now make the following conjecture that the set of Coulomb branch operator and the set of Schur indices, this specifies your aCFT, then what you get is that to specify this, you need a finite set of rational numbers. And if you give me this set of operators O, I can compute the Schur index and the corresponding linear modular differential equation that is also fixed up to a finite set of rational numbers.
Sorry, and on what indices does the family of Schur indices depend? Because you give a definition of one Schur index, but that's so. I mean, I thought that there was a single Schur index. You say that there are many.
No. There's a single Schur index for your theory.
Okay.
So what I mean by assigning, perhaps what I meant is not that there is different ways of defining the Schur index. Of course, if you give me a different set of operators, then these coefficients will be actually different in the Schur. The Schur indices would be different functions.
So a theory will be defined by one Schur index and a family of O.
Of yeah. Okay, and so this guy is defined by a finite set of rational numbers because of these properties. Once the Schur index is in fact an infinite series, so it's not defined by a finite set of rational numbers. But the point is that there is this highly non-trivial thing that this function actually satisfies a linear modular differential equation, which is instead specified by a finite set of rational numbers. So the end of the day is that you basically have a finite set of rational numbers specify your entire aCFT.
But it's unclear to me like why only these operators would fix the entire all the operators in the two-point functions that you have. I mean, if you have a Lagrangian, usually supersymmetry constrains it to a few terms, and then you have a few coefficients.
Yes.
But if you have non-protected operators, like it's very non-trivial to calculate their dimensions from this.
I agree. I mean, so I agree. So this is a conjecture, and I think it's purely based on the fact that there is a total absence of counterexamples. But I agree with you that it's a much more non-trivial question that given this set of data, you can actually fully solve the entire thing. Because that's what I mean. That's what I'm claiming that this finite set of rational numbers specifies the entire spectrum of your theory, including non-protected.
So these are short multiplets, right? Both, I think, right?
They're all short. They're short.
So, but you say that it's sufficient to fix these short multiplets, and then the long will follow for free.
Yeah, that's what I'm claiming. I mean, in other words, basically, to me, there's only two possibilities, right? Of course, either that's the case or it's not the case. I mean, that's not inside. But that if you take the one that sounds more reasonable, right, which is the fact that a finite set of short multiplets doesn't fix the whole set of non-protected operators, and you take it to its extreme conclusions, then you reach a very non-trivial point that really, when we talk about low rank, for example, aCFTs in 4 dimensions, we really only talk about the protected sector. So then if you actually are claiming that the protected sector does not really specify the whole theory, that means that theories that we have considered to be unique, they in fact can correspond to an infinite set, or perhaps a much larger set of theories, which are only different for the long multiplets sector.
And another thing is, you specify independently the Schur and Coulomb.
Oh, that's a great question. No, that's a great question. But this is highly, I would say, still mysterious thing. There's a relation between the Schur index and something that you can compute from the Coulomb branch. But that relation is highly non-trivial. So it's clear that they contain the information they contain is not mutually it's not completely independent. They share information. The extent by which they actually share information, that's not clear.
So it's not known which sets of this actually correspond to some specificity, right?
Right. So that's what I'm right now in the last 6 minutes. I'll tell you a way to basically start from finite set of rational numbers, and then get a set of conditions so that you actually can produce aCFTs. But sorry.
I was gonna. Is there any way to like prove this conjecture? Is there any idea? Or just an open question.
No, I believe I think many. I mean, so no, I was discussing it with Chris Beam extensively in Oxford. We made zero progress.
You can prove it in very specific case using Bootstrap. But only that's for large class of theory. For a single theory, you can try to prove it using Bootstrap.
Because I was thinking, for instance, in N=4, you use integrability, then you can calculate.
Or with more
you have some more ingredients.
So for like the rank 1 theory, the Mario was describing, where scaling dimension is 6/5 on the global edge, that has been proven using Bootstrap.
For all the operators.
I mean, for some non-protected operators.
For some, yeah. I mean, I'm willing to bet on this. I'm willing to, the fact that this specifies a whole theory, I'm willing to bet on. I know that it's not convincing. I'm telling this, but I prove it. I'm giving you no evidence. But it's really, it would be really mind blowing if we only discuss the protected sector, and that each one of these points that we consider to be unique theory instead correspond to a large set of theories differ only by. They would be truly short. Okay, in the last 5 minutes, I have 5 minutes, is that correct? Yeah. So then let me sketch this. This is something that we published quite recently, and it's an interesting exercise to be able to go through a list of those assignments. Okay, so I'll be just brief since I have 5 minutes, and what is the idea? So the idea is that you want to, the problem that you can solve somewhat algorithmically is that you look for sure indices which satisfy a linear modular differential equation of a fixed degree, order k, you fix the order, and then you want that this is interpretable as a theory with R Coulomb branch operator. Okay, so you look at one value of k and R. You have to pick up the k and R, and you do the search for those two values. Okay, so then you fix k and R, so these two values, and you look for it, right? So the way you look for those is by inputting numerically some initial factors of the Schur index, just the first 4 or 5 or 6, enough to fix all the coefficients of the order k linear modular differential equation. So you're inputting finite numbers of integers, just some random things, like you're just checking, you're inputting some random guesses, and then you want to look in retrospect if it's correct. So the input is the first few terms of this putative Schur index, and then run the thing. That means basically implementing some of the constraints I told you and many of the constraints I didn't tell you, and then you have as an output those initial guesses that are consistent. Now in our paper, we fixed k equal to 4 and R equal to 2. That's an easy thing, but nevertheless, we scanned over, let me have the exact number, I think it's 10 to 11 Schur indices, and found 8 solution, which only 8 were passed the test, but of which 2 were not rigorously excluded, but they are more, they are very unlikely, and so the remaining 6 were sure indices of known theory. Okay, so
10 to the 11, how much is, what's the parameter space? Is that the whole thing, or is it just some random number?
no. So there is a way to order this thing, and it's the fact that it's a little tricky. So here there is the coefficient of this first factor is telling you the dimensions of the flavor symmetry, right? And so then if you have this factor to be a certain number, then everything else has to fall in representation of this particular flavor symmetry. And we put an upper bound on the dimensions of the flavor symmetry of the theories that we were looking for, which I thought was something like E8 cross E8 or something like that. So that's clearly an upper bound, but we've been consistent in searching this well-defined parameter space. Okay, so well, anyway, so I think I've got to wrap it up. And so the point is here, well, I'm giving you a sense that, in my opinion, there's a lot of the type of constraints that you have in 4D aCFTs are mature to really be leveraged in such a way that you can really start milking what is allowed by superconformal invariants in 4 dimensions. And again, I think the key point is that this is a key point, and also something that we conjecture an assumption that your aCFT is specified by a set of rational numbers, and there's a ton of constraints, self-consistent constraints that allow you to start with a finite set of rational numbers and go from 10 to 11 to 8.
Sorry, I have a question. You reported us about the rational numbers deltas conformal dimension. What about the lambdas of those?
What are the lambdas?
Lambdas use a structure constant. Lambdas
OP coefficients.
Oh, right. That's what. Again, that's a great question. So the OP coefficients don't enter the story at all.
Can you compute them?
That's no. At the moment, there's no. I mean, you can compute. There are tools that can compute it, but certainly not with this approach.
Some of the OP coefficients are known from the Schur
algebra. But for other kind of
For other, you know the Caroline coefficients, but you don't know the 2-point function. So 2-point function is more abstract. Because you need to normalize operators before doing the physical 3-point functions.
Thank you. So I have 2 questions about this. First thing, these 6 known theories, are they Lagrangian?
No.
Or do you have some or none? So
I think there are 1 or 2 that are Lagrangians. But the overwhelming, so for example, this can be done. You can restrict. There is a kind of a little orthogonal classification. That can be done. You can ask. Let's say that I want to restrict to theories that only have 1 Coulomb branch operator. We call it those rank 1 theory. Now there is a way to, since it's particularly simple, you can classify this purely geometrically using slightly different methods. So and in this setup, you can ask. Okay, we believe that we have a complete list of rank 1 theories. You can ask how many of those are Lagrangians and how many of those are not Lagrangian. And you find a list, I think, 28 theories in which only 2 are Lagrangian.
So how do you find the non-Lagrangian one? How do you know that they exist?
Okay, so that's great. So there's various methods. And I think you really have to kind of like see that a given you find some periodic theories in one method, and hopefully a second and third methods also work. So what are the possible methods? So of course, initially they could be engineered in string theory. So you could put some particular setup of D-brane and so forth and so Then another thing that's very famous is that you can move on the Coulomb branch of Lagrangian theories. And now Lagrangian theory usually has relevant deformations. So you can do RG flows that are complicated. So you turn on some vebs as well as some mass parameters, and then you kind of engineer things in such a way that all of a sudden on the Coulomb branch there are some particular singular points which are identified as aCFT, and those are the famous Argyros-Douglas theories. And then there's the bootstrap that Ethan has. So those are all tools that don't require necessarily. And then you find evidence for these theories, and then you find the same evidence for the same theory using very different methods, and so then the kind of the confidence that there is an actual fixed point of that kind increases.
Do you expect to find many new 4D theories using this, or are like most of the 4D theories are known?
So first of all, I mean, of course, you can find new 4D theories if you increase the rank indefinitely. I mean, that's also for Lagrangian theories. So the question is, to me, is restricting the rank. So you look at a set of theories that have some fixed. You have to fix something, and then you look how much do we know about those theories. In my opinion, for example, in rank 2, which is two Coulomb branch operators, I think we're close to probably know the full set of theories.
It is so a consequence of your conjecture is that there is no theory without the Coulomb or Schur branch.
No, so that's great. So the Schur branch here, it's possible that, as I said, the one that acquire them is a scalar component of the Schur operators, and there's certainly some Schur sector in which it's the scalar component is empty, so there is no Higgs branch, but nevertheless there is some non-trivial stuff in there. So that's something we know, and
so you have studied the case where there is no Coulomb branch and no Higgs branch.
No, so that I claim that there isn't any. There isn't any. There's mild evidence.
And there is always modular space in C.
Yeah, but that's there's no proof of that. There is. I have mild evidence. I have some non-trivial evidence.
So that doesn't actually happen. It's very counterintuitive because in 3 dimension with same amount of supersymmetry, there are examples which have no modular space.
Yeah.
3D into 4 theory, there is an explicit counterexample. But somehow in 4D into 2 with the same amount of supersymmetry, there is no counterexample.
There is no counterexample.
Maybe that's just because you have not. Like,
I think I will push it. I push it against the fact that it's just because we haven't found it yet. But I agree. I see your point.
But maybe following up on Massimo's question. So in this case, if you assume the Schur index just 1.
Just one.
Just 1. So no non-trivial Schur operator. Is there any inconsistency?
Yeah, because the stress tensor is.
It will contribute.
It contribute. I mean, again,
the
story
that
there's yeah, exactly. The stress tensor multiplet
so it
contains
cannot be 1. Yes.
Yeah.
But can you take it to be just the?
But I think these are the vacuum module of minimal models, right?
Right,
The 2, p minimal model.
Vacuum module.
The 2, p minimal model.
Right.
Those are the ones.
Yeah.
So now you have this data. Can you feed them to the people who do bootstrap, or I mean, how do they use it? How could they use them?
Yeah, that's a good question. So unfortunately, I mean, those are a little bit orthogonal approaches, and we're really using here this linear modular differential equation stuff. That it's really kind of a more analytic. It's not a numeric approach, and it's really. This mapping is called, it's the story of vertex operator algebra. So usually the way in which the vertex, so there is a very interesting, intriguing fact that you can start your 4D theory, and if you restrict your operators on a plane, and you only restrict to Schur operators, and you do something on something else, you find a subsector that basically is a chiral sector of a 2D CFD. And that's where many of our kind of analytic constraints come from. The way in which the bootstrap uses this is what Yifan was saying, but it's much weaker things. You fix some coefficients by doing this analytic stuff, and then you just implemented it in your numerics. But your numerics really run kind of in the old way. So in some sense, they're very kind of orthogonal.
Yeah, I see. So n equals 2 supersymmetry, and into superconformal doesn't
No.
give you any.
In fact, I mean, and perhaps even you know better, but like there is it's remarkable how little that gives you. It just doesn't seem. You can derive some bounds, but it's really kind of like compared to what I described. It's very.
Is there a nice understanding of where these numbers come from geometrically if you compactify a 6D theory?
Which numbers?
The set of rational numbers that you use. Like, is there a geometric understanding?
I wouldn't know. No.
There is a deep relation. So from the 6D construction, the 4D theory will be associated with the HE moduli space. And all these rational numbers, both on the Coulomb branch and on the short sector, will be related to the HE moduli space. It's on paper from the Coulomb branch that is understood. From the Higgs branch.
But for example,
we'll be discussing the paper from Foucault and Pei.
So, what about the coefficients? I mean, the coefficients of the linear modular differential equation. Is this?
I don't think that part is discussed explicitly, but there's some similar discussion. You can check this paper from Foucault.
No, that would be extremely interesting. I mean, because you're saying beyond just the kind of vanilla class S, which you're just saying.
The H modular is not supposed.
Okay. I mean, that would be extremely interesting if because I think that the rational numbers specified in the linear modular differential equation, those are really the ones that are less physically kind of transparent to me. So if there was a way to get it from 60, that's interesting.
Thank you. All right, thank you. Let's thank Mario again.
If n equals 4 becomes trivial, or
yeah. So n equals 4 becomes trivial. N equals 3 is interesting. And one of the reasons is that for n equals 4, you